Recording in progress.
Nice. Okay. Welcome to week 2. What's the plan? Today I'm just going to. Oh, you want me to speak up? Oh, yeah, sorry, yes. Goodness. Uh, yeah, week 2. Most of this week will be spent on spectral sequences. If by some miracle I manage to finish whatever I wanted to say in 5 days, we can talk about something else like derived categories. Except the problem is I know very little about them. So whatever happens on Friday is whatever happens. Okay. But for today, we're going to do just mostly terminology and some motivation. And then maybe tomorrow we should do some calculations. Okay. So double complexes. We're not going to use these immediately, but we need to know about them in the future. So, okay, let's start. I'm going to be doing everything cohomologically. So I apologize. I realized the first week a lot of it was homological, but now I'm going to flip it. If you want to see what happens in the homological point of view, it's all in Weibull. I flipped everything for my own personal taste. Okay, so a double cochain complex. Let's do it in abelian category. So this one is abelian. Okay, so well, it's a double complex, so it's indexed by 2 entries. I write C bullet bullet. This is a collection of objects CPQ. So of objects of A, and then it's a complex. I need the differentials. So with the following maps. So okay, I have horizontal differentials and I have vertical differentials. So D sub HPQ, this goes from CPQ to, okay, so it's a horizontal differential. So it's CP plus 1Q. Yeah. And then there's also the vertical differential. So DVPQ going from CPQ to CPQ plus 1. And these are differentials. It should be a chain complex in each column and row. So such that. So if I do it twice, so DHP plus 1Q, DHPQ, that's equal to 0. And then similarly for vertically, so DPQ plus 1, DPQ, so the vertical ones. Hopefully I got the order right. Yeah, that's also equal to 0. And then there's this other condition that we're going to also enforce, this anti-commutativity of the squares appearing. So okay, what is this condition? And so this is the odd one out. This is, so dv, so okay, this is p plus 1q, and then dh pq plus dh pq plus 1, and then dv pq, that's equal to 0. And then, of course, everything is for all PQ. Okay. So what does this look like? It's much easier when you actually draw the double complex out. So here's the picture. Okay, this will take me a while to draw. Bear with me. So, okay. I'll start with the central node. So that's CPQ. Maybe we'll just fill in the rest. So above it, Q is vertical. So CPQ plus 1. And then below it is CPQ minus 1, right? Yes, good. And then horizontal is P. So then over here, I get CP plus 1Q. Up here, I get CP plus 1Q plus 1. Down here, CP plus 1Q minus 1. Of course, back here, P minus 1, Q minus 1, P minus 1Q, and then CP minus 1Q plus 1. Great. And so the horizontal differentials go this way. And maybe I'll just label one for sake of example. This one is going to be DH. Well, okay, it's labeled by the starting module, so P minus 1Q plus 1, of course. And the vertical differentials go this way. And yeah, this one is dVPQ. Sure, fine. Okay, so right, I mentioned earlier that, okay, each row column determines a cochain complex in its own right. So restrict to the, you just use the horizontal or vertical differentials. It gives you a cochain complex. And then you get anti-commuting squares. Oops. Anti-commuting squares. So yeah, great. Okay, so now some more terminology involving double complexes. So terminology. So we say a double complex, oops, is bounded if, okay, I should label it. So oops, C bullet. If C bullet has only finitely many terms along each diagonal. So that is to say, so for each n, there are finitely, or sorry, I should say non-zero. Of course, non-zero. Finitely many non-zero CPQ for which P plus Q is equal to N. Right. And throughout, we are just going to focus on first quadrant double complexes. So on so-called first quadrant. So that is C bullet where CPQ is 0 if P is less than 0 or Q is less than 0. So these are just concentrated in the first quadrant. If you think of the PQ axis, everything only lives here, like this, more or less. Yeah. And of course, these first quadrant complexes are bounded, right? Each diagonal only has how many? N plus 1. Yeah. So 0 has 1. The second diagonal, or geez, okay, I'm gonna count it wrong, but it's one more then. Yeah, question.
When you say diagonal, you specifically only mean the like decreasing diagonals?
Like this.
Yeah.
Yeah. So P plus Q equals N, and yeah, those are gonna make these types of lines,
Okay,
right?
so those are the only diagonals you care about.
Yeah.
You don't care about the other ones.
Yeah. Right. We're not going to use, like, okay, when you will see in like the next slide why I'm only gonna worry about this.
Okay.
Yeah. So just these. Okay. Okay, let me just check on the Zoom if everything is okay. Good. Okay. So why do we do all this? Why, okay, maybe even further back, why this anti-commutativity of the squares? Well, I'm going to define something called a total complex. So, okay, total complexes. And here you can think of just, so we can look at double complexes in R mod, or if we were doing it in an abelian category, I should worry about, okay, I'll write this down and then I'll make the remark. But yeah, okay. So to a double complex C bullet, we can define, so the following total complexes, there are two of them. There's product C bullet, and then there's the total with the direct sum C bullet. And these are defined by, so so these are cochain complexes, and so I should define what each module is in the complex and the maps, right? So okay, so total prod C bullet is equal to, you might expect the product P plus Q equals N, CPQ. So this, okay, maybe if I draw a picture like this is just a sketch. All this is doing is it's just taking one of these diagonals and just taking the product of the modules appearing in that diagonal. And you might object, like, can I do this? What if there are infinitely many? We only do this in so-called complete and co-complete. Well, okay, this one for complete and then the next one for co-complete abelian categories. So, okay, next definition. This is total direct sum, and you can guess it's just direct sum. P plus Q equals N, CPQ. And now what is the differential between, oh, I should have an N here. Yeah. Yeah, okay. So what is the differential between any two of these modules? So we have this dn. Okay, so well, okay, the book writes it like this. D, if we define D by this dH plus dV, whatever that's supposed to mean. Okay, you can attempt to unpack this. I struggle a little bit with chasing maps, but you can believe it's not too bad. Basically, I'll draw the picture first, and then maybe you can figure out how to write it properly. Okay, so if I just take, so let's look at just, I should probably copy, no, maybe I'll copy this picture here. Just for the sake of illustrating what this map is. So let's just pick this one to be, so this diagonal to be the one where P plus Q equals N. So this is degree N modules. And so I need to define a map between here and maybe I'll use a different color. Here, I need to define a map going from the yellow to the blue. And so how can I do this? Well, I've got to use the horizontal and the vertical differentials in a certain way. And it's basically just, if I have a tuple here, so, oh dear, I should pick a different color. Maybe green. So if I have something here, or maybe, I don't know, I'm gonna mess this up, but basically if you have elements here, here, and here, you just sort of see what happens to them when you apply the differentials, and you just add it together, basically. You can probably write it down as like some horrible sum, P plus Q equals N of the direct sum of a bunch of zeros. There's probably like equivalent ways to do this. And then you can direct sum like the differentials with the right indices, blah, blah, blah. You can figure it out. It's not bad.
So a guy in CPQ just goes to the guy in CP(q+1) plus the guy in CP+1(q). Like.
Yeah,
that-
yeah, I mean,
So
yeah.
just splits a little bit.
It just, yeah, it takes an element. So, okay, if we're just looking at one, oops, at just the one guy, like you were saying. Oh dear, I lost it, whatever. Yeah, if we were just looking at this screen bit here, it's just this plus this. The right plus. Yeah. Okay. So that's that differential. And so then the question is like, okay, is d squared? Okay. Is d squared equal to 0? You can check, yes, it is. Just do this twice. Use the anti-commutativity of the squares, dot, dot, dot. Yeah. And so now the question is like, okay, if I wanted to compute the cohomology of such a horrible complex, this might suck. And so there is sort of a way to do this. The usual, I don't know if this is the usual way to do this. This honestly seems a little contrived to me, but you can do it with a spectral sequence. There is a way to do it. But we will actually return to this, this concept later, meaning the calculation of the cohomology of a double complex using a spectral sequence. So, okay, where was I? I feel like I'm forgetting something to say. Yes. So, okay, if I have a bounded double complex, then these two coincide, right? Finite products agree with finite coproducts. Great. Okay. Cool. So yeah, we'll return to double complexes later. So now I want to talk about some maybe vague motivation for spectral sequences. So, okay, motivation with a question mark for spectral sequences. So, okay, maybe really I should be doing this example with topological spaces, but I've refactored everything without the topology. It's just, I'm just looking at the algebra that's going on. So consider a short exact sequence of cochain complexes. Maybe it looks like this. So 0 to A bullet to X bullet to X mod A to 0. And so to a short exact sequence of complexes, there is the long exact sequence in cohomology, right? So, okay, obtain this long exact sequence. It goes like this. I've written this down maybe a few times now, but I'm going to do it again. Hn minus 1. So, oops. Okay, this should be X mod A. Next to Hn A to Hn X to Hn X bullet mod A bullet, and so on and so forth. Oops, plus. And there's this philosophy that like, okay, maybe if I knew the cohomology of A bullet and if I knew the cohomology of this quotient here, I could use exactness to figure out the isomorphism classes of the cohomology of X bullet, right? That would be great. But what if I wanted to sort of, I don't know the right word, iterate this process? There's a way to sort of do this again in a very particular way, which I'll write down. Maybe I'll just write down the next step in the process that could be considered like an iteration. So, okay, what if now instead I had two short exact sequences, the following two short exact sequences. So what if we had two short exact sequences? So the one that I'm going to write down, I'll do it in a different color. I need both colors. You'll see. So 0, A2 bullet, A1 bullet, and then A1 mod A2 to 0. And then in blue, it'll be 0 to A1 to X. And then, so I mean, the same short exact sequence from before. So X mod A1 to 0. Yeah, indices are correct. Yes. So now I can get two long exact sequences in cohomology, right? But I'm going to sort of sew them together in a funny way, or at least graphically to start with. So we'll do the blue one first. So dot dot dot. So H and A1. I'm gonna suppress the bullet. It's too much. H and X. And then H and X mod A. And then this will connect to Hn plus 1 A. I'll do this weird staircase thing again, Hn plus 1 X. And then dot dot dot. Or maybe I should have one more term. Let's say Hn plus 1 X mod A. And then dot dot dot. So that's the one coming from the blue short exact sequence. Now I can stack on top of this a similar one for the red short exact sequence. So like this. Oh, I should have some more space. Like this. So Hn A2. But I'm going to use this term. So I don't want to overwrite it in red, but this is part of the long exact sequence now. So I've like, this is what I mean by sewing them together. Somehow I've at least graphically done it like this. So then Hn A1 mod A2, and then here should be Hn plus 1 of, oh, I forgot the numbers here. It should be 1. Yeah. And then here should be A2. Yeah. Right. Right, A2 to A1. Yeah, exactly. And then going this way, now I get connected to Hn plus 1. Oh, now it's A1 mod A2. And then so on and so forth. And so you can maybe imagine, like, if you had 3, 4, however many, right? I'll talk about that in a second. But it's interesting. You can sort of do this stitching, and maybe the stitching isn't super convincing, but what is convincing is maybe, if you had information about the cohomology of A2 and A1 mod A2, you could figure out the cohomology of A1 bullet. And then if you knew the cohomology of X mod A1, then you could soup all of this together in some fun way, using a bunch of exactness arguments, whatever, to get the cohomology of X. But we want to sort of generalize this in some sense. Maybe you notice that you can define some kind of map here from Hn X mod A1 to Hn plus 1 A1 mod A2. You can define a map like that, which is just the composite of the two maps. And then you might define a collection of maps like this, and somehow they piece together in a certain way, and actually they form differentials. And then you might ask about the cohomology of this, and you can get a lot of data by doing this weird stitching thing. What to do with all this data, it's curious, but somehow the motivation is that, like, you can, how should I say this? You can approximate the cohomology of X with this data in a different way, and this is the using spectral sequences. So little bit shaky. I will return to this. This notion leads to what's called an exact couple. So if you do topology, you would have seen this. I've never seen this, so bear with me, and if maybe tomorrow or the day after when I get to this. Yeah. Okay, and so okay, what is the natural generalization of this? You can keep going. You can keep going. If you started with, say, some kind of filtration of the form, so filtration of X bullet by, so something like this. You could have something like this. AM bullet going into yeah, -1, decreasing. And all the way down to a 0 bullet, which I'm going to call X bullet, something like this. And you can keep making these, you can like make the short exact sequences out of this filtration by just forking them over like this. So AM -1 mod AM, and then over here it's A0 mod A1. This, yeah, oh, wait, that's that. And so with all these short exact sequences, you do this funny thing, and ... spectral sequence will appear, approximate the cohomology of X bullet using the data that we can find. So yeah. What do I mean by approximate? So there is a way to recover parts of the cohomology of X. So I mean, so the associated graded modules of the cohomology of X. And then, yeah, we have to piece them together. So I've used this terminology that I will have to define shortly. So I'm going to write this down. We can use whatever a spectral sequence is to recover the associated graded modules of the cohomology of X bullet. And so then it's like, okay, I haven't defined what associated graded modules are, but the punchline is that now the problem is you've got the cohomology of X bullet now up to extension. You have to sort of put together these associated graded modules in a, I mean, you have to know how to do that to recover the honest cohomology of X bullet. Now, not so bad in certain cases, which I'll write down in a bit. Okay, so now I should define these words. Maybe it's worth reminding us what I mean by this graded language and all. Okay, so by a Z graded module, I'll do Z graded modules, rings, and even algebras. But I don't think we'll need algebras. It's just a curious natural extension of the definition. So graded module. So a graded module M is, or sorry, a graded R module A, which I'll write a star here, is something like this. It looks like the direct sum over n in the integers of an, where an is an R mod. Fine. But you know, these things should define a category. I should be very careful with what the morphisms are. And so the morphisms in this category of graded R modules are the so-called degree preserving morphisms of R modules. So the morphisms are degree preserving. So by degree, I mean, so we say, okay, Wow, I have everything in the wrong order. Okay. So we say that elements of AN are homogeneous in degree n. Okay. So the morphisms are degree preserving, that is, they're just a product of morphisms from AN to BN. Or AN to, okay, yeah, AN to BN, where direct sum BN is another graded R module, B star. Okay. Okay, so now a graded ring. Okay, I'll just do ring. I'll replace with algebra in a second. We won't need algebra, so maybe honestly, I probably just won't do it then. No reason to. So graded ring is a graded Z module, so graded abelian group with, so now there's this degree 0 map that goes from A star, now tensor. Okay, what is this tensor? I'm not going to define it in general, but in this particular case, since it's just between the two, I mean, it's no different from the usual definition, but it's the direct sum over P plus Q equals N of AP tensor AQ. So from this to back to A star, and this map is just some kind of product. And I insist that this product is associative, unital, whatever it needs to be. And this is equivalent to just saying that A star, so okay, this is a great C module, A star with this product. And another way to see this is just to say that A star is the direct sum of the AN, and it has the usual structure you probably are used to if you like polynomial rings, for example. So AM dot AN, so maybe I call this the dot map or something. This is contained in AN plus M, as you might think. And so topologists have seen this. So the usual example in the setting is the cohomology ring of a topological space. So I won't say anything about that, but yeah. Okay. And so I mentioned filtration earlier. I will need that word to define this associated graded nonsense. So filtrations. Modules. So a decreasing filtration of a module M is the following. So somewhere way over on the left is 0. That's contained in some modules. And now I'll start indexing them for realsies. So let's say F1M, that's contained in F0M, which is contained in F minus 1M, all the way up to so on and so forth. And then all of these are contained in M, which here will just be the union over N of F and M. And so typically what we'll see is that these filtrations are bounded below, bounded below filtrations where F0M is just M. So yeah, it just stops at F0M. Cool. And so from a filtration like this, you can obtain the associated graded module. So this is denoted GR star M, which, well, it's a graded module, so it's just the direct sum of the grn of m and the grn of m are these quotients, just like from before, or similar to before. So this is fn m mod fn plus 1m. Right, fn plus 1m is contained in, right, because the decreasing filtration. Hopefully I did this correctly, because in Weibull, everything is homological. So it's like all flipped. They use the increasing filtrations for this homological setting, and then the decreasing filtrations for the cohomological setting. So, okay, great. And so what is the point? So the point is, in some sense, gr star of m approximates m in some sense. But it's only an approximation because of these extension problems. So you can have a filtration like this. So okay, extension problems. So maybe your filtration is like 0, z, inject into z. And that's your m, maybe. Yeah, that's how I want to do it. So then if I calculate the graded pieces, what are these? The associated graded, or okay, I want the pieces of the associated graded module. So the gr, grn's of m. So this is this of z. I might get something like, okay, I'll just write what I should have, and then I'll write the isomorphism down. So f1m, f0m. You can write down a Schur exact sequence like this. So this is f0m. Oops, 0 goes up here. f1m. So this is the gr 0m. And this one is the gr 1m. Right? Yeah. And this is just m, which is z. This one is also z. So now it's like, okay, what is this? How did this? You need to know what this is, and then different things can happen, right? This could be a split exact sequence. This could be non-split, right? Lots of things could happen. So so the graded pieces. So okay, the graded pieces. The graded pieces grnm are not enough to determine but maybe there are some nice settings if you're doing everything with vector spaces, every Schur exact sequence of vector spaces splits. That's great. So maybe if you're doing everything over z mod 2z, or the reals or the complex, fine, whatever, not so bad. Maybe your R is not a field or whatever, but maybe you got lucky and your graded pieces G, R, and M are free or projective or something. Then you can make you can make sections or whatever, and that would also be okay. That's also a nice thing that you can hope for, maybe. So it's not all bad, but it's just like that. Okay, how am I on time? Yes.
So the associated grade is not, it depends on the filtration. It's not uniquely determined.
Right. It's based on the filtration. Yeah. It's 4:43. How many more do I? Okay. Okay. So just looking at what's ahead. What's ahead is just the definition of a spectral sequence. It's possible I don't get to everything. There's a lot of jargon, unfortunately. So what remains in today's lecture is just going to be the language for spectral sequences, and it's possible I don't finish. which is okay. So, okay. Right, so now we're ready to define cohomological spectral sequences. So a cohomological spectral sequence, starting at EA. So here A is bigger than or equal to 0, is a family of objects. So ERPQ, they form a grid. And there are several grids. So I have this R on the bottom too. So R here is bigger than or equal to A. And maps. So DRPQ going from ERPQ to ERP plus R Q minus R plus 1. Yes. Which are differentials in the sense that, okay, I'll just say that d squared R equals 0. So for fixed R, if you take two of these differentials, if you have two adjacent differentials, if you compose them, you get 0. We'll see that in the picture. I'll draw in a bit. And then furthermore, how are the objects between, so if R is A and then I go to A plus 1, how are the modules related to each other? So furthermore, there are isomorphisms going like this. So E R plus 1 PQ. This is just given by the cohomology of the previous, how do I say this correctly? It's easier with a picture. It's just the cohomology at the same spot in the previous R. I want to say sheet, okay. I'll use that word in a bit when I draw the picture. The picture is much better. This is horrible. So this is the cohomology at the previous stage. So this is kernel dr pq mod the image of, okay, what's the map going into the pq spot? That's dr p minus r and then q plus r minus 1, right? So then if I subtract r and add 1, that goes to q. Yeah, great, good. And like with the double complexes, typically we will just look at the first quadrant one. So like with the double complexes, typically, oh, the screen. Is this the 10-minute warning? Yeah, let me turn on the screen again. Typically see the first, oh, wait, let me wait for the screen to come back on.
I think it's just the white fluid.
I see.
So these first quadrant spectral sequences. So that is ERPQ is equal to 0 for P less than 0 or Q less than 0. So all the modules are concentrated in the top right. Okay. Okay, that definition sucks. We should look at a picture. And I'm gonna have to draw the picture like 4 times or something, 3 or 4 times. So, okay. So the picture, and I'm gonna try to draw it very clearly. So I apologize, this will take a little bit. At least the first time it will take a little bit of time. So let me just write down the differential just to have this up here. So drpq goes from erpq to erp, geez, It's plus r, and then q minus r plus 1, right? The cohomology, yes. And so, okay, so now, okay. Oops, how many do I want to draw? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I'm going to draw a p-axis and a q-axis, and I'll label this E0 star star. Okay, and here, I'm not going to write in the name of the module. I'm just going to draw like dots. So this one is E0, 0. This one here is, which should be E1, 0. E2, 0, so on and so forth, right? And then this is E0, 1. You know, you just fill it out like a grid. Okay, maybe I make these bigger. I hope this is enough space between the dots. Okay. Great, so those are the modules appearing there. You should imagine that they'll have the subscript 0 or whatever. And so now what are the morphisms, the differentials between these two? So, okay, the picture, at least for first quadrant, because it's going to be miserable if I draw it in general. So, okay. So D0 PQ goes from EPQ0 to E, well, R is 0, so it's P, and then it's going to go to Q plus 1. So it goes vertically up once. So the maps are like this. Okay, so this is the zeroth sheet or page. And so now how to get to E1, you take cohomology. Jesus, cohomology at each node. And whatever you get, you put that into that spot. So, okay. So now I have to duplicate this picture. Because the same picture, I'm not going to label the red dots, but now the maps are different, right? So it's like this. So now each of these red dots in the second page, or, well, okay, second page, it's E1 page. So E1 star star. So in here, so D1 PQ goes from E0 PQ, so sorry, E1 PQ to E, so P plus 1, and then Q plus 1 minus 1 is Q. Yeah. So, okay. And so this just goes horizontally like this. Okay. Take cohomology again, you get the next page and so on and so forth, but I'll do one more and then you know, at this point you could see the pattern of how the shape of the maps, I guess, the angle of the maps, they change, which is, yeah, so E2 star star. So, okay, erase these. This time I won't bother writing down the map. I think you see what's going to happen. So, okay, I might as well. E2 is a little different. So D2 PQ goes from E2 PQ to E2, okay, P plus 2, Q minus 2 plus 1 is Q minus 1. So across 2 to the right and then down 1. So they look like these. And then, I mean, I don't have more red dots, but this one would go over there or wherever, but so like this. And so basically we will, you keep doing this, and so how do the differentials change over time? They do this weird process. They look, the shape is like this. They get longer, they start pointing more down, more over to the right, so on and so forth, blah, blah, blah. And you just keep taking cohomology. Okay. But since we're looking at these first quadrant spectral sequences, something nice actually happens. So, everywhere on the side, so over here it's 0, here it's 0, this quadrant also 0. So at some point, all of these maps going out of the red dots, they are going to land in a 0 module, right? Because the arrows just get longer and longer, and they keep pointing down. I mean, if you don't believe me, just follow the pattern, count it, and see how long it takes. It doesn't take that long. So eventually, each one each of these maps will go to a 0 module. So, okay, so I should write that down. So because these are first quadrant spectral sequences, eventually, so what I mean by eventually is eventually in R, the differentials dr become 0 maps. So, I mean, two ways to, I've omitted a lot of the other differentials, like any arrows that I didn't draw in the pictures above, like over here, coming from the 0 modules, etc. I omitted those, but in general, what'll happen is every arrow that appears in the sheet will either be something like this, going from a non-zero, possibly non-zero module to 0, or from 0 into, maybe I can just make them red to match the picture. So it'll go from a red dot to 0, or 0 into a red dot. That will eventually happen. So at that point, then when you take cohomology, it's kernel of the map going out of the red dot mod the image of the map going into the red dot. So nothing actually happens, right? So at that point, it stabilizes at that node. And so we give a name to that. Maybe I'm getting ahead of myself. This is weird somehow. Oh, okay. Well, okay. The reason my notes don't match what I'm saying is because this phenomenon is also true for bounded spectral sequences. The same happens for bounded spectral sequences, right? And so what will happen, what we write is that in this case, we write, so we say the EPQR stabilizes to what we write as E infinity PQ for each PQ, right? So this E infinity PQ is just whatever it ends up being after however many sheets you progress to, however many that is. It's, if in the case it doesn't actually get to the stage where the differentials become 0 maps, it's some kind of co-limit. I don't know. We're not going to worry about it. So Okay. Okay, so now how much time do I have? A minute. So maybe I will just stop and come back to this terminology later. Yes,
I have a question.
sure.
So I remember that when I learned about spectral sequences when I was doing algebraic topology, the only thing that anyone cared about, maybe for just the Sayre spectral sequence, was page 2.
Yes.
And after that, no one can, like, it doesn't even matter anymore. They just look at the infinity page.
Right, yes.
Is that true more generally?
Apparently, I don't, I'm not a topologist. I don't actually,
Yeah, not it wrong.
yeah, I mean, this is, I've read that this is the case. I guess so.
I see.
Most of the time, okay, what I've read is that indeed, like you say, most of the time, these spectral sequences stabilize at like page 1, 2, or 3 or something. Or maybe they don't stabilize at page 2 or 3, but it's enough to get you whatever information you wanted.
I seem to remember that a lot of times you would have, while it may be really long in like the horizontal direction, like there just aren't that many vertical ones.
Right.
The line of the vertical is just.
Yes, yes. So if you have a few, like, okay, there's an example. I will get to this next time, but if you had like one row or one column, it's very nice.
Stabilizes.
It's like that is what happens. Yeah, it's stable at that point. And yeah, it's just a chain complex. And so I will get to why that's more nice next time, but nice things happen. Yeah. Okay, maybe I'll stop recording so people can leave. See you next time.